Hi. So we've already seen the definition of a matroid in terms of independent sets. And then we saw in the last lecture that we could also define a matroid in terms of its bases. Today, I want to show that we can talk about something called the circuits of a matroid and define a matroid using its circuits. We'll also see that this definition is really well suited to the rigidity matroid and proving things with the rigidity matroid. Okay, so let's get on with it. I want to start by defining what a dependent set of a matroid is. So suppose we have a matroid, so we have a non-empty finite set E defined using our original definition. So a non-empty finite set E and I, which is the set of all its independent sets. We're going to define any subset of E that's not in I to be dependent and say that a minimal dependent set is a circuit. So that a set is a minimally dependent set if it's not independent and it doesn't contain any proper dependent sets. So for example, let's consider this linear matroid right here. So here we have 4 vectors in R2, 1, 0, 0, 1, 1, 1, and 0, 0. And we'll define the linear matroid on these vectors. So that means that the independent sets are the linearly independent subsets of these vectors. So let's think about what are the circuits then? Okay, well, these vectors are all contained in R2, which has dimension 2. So any subset of 3 of them has to be dependent. And in fact, we see that the set containing 1, 0, 0, 1, and 1, 1 is a dependent set, and any subset of it is linearly independent. So this is a circuit, Now, any set of more than 2 vectors in R2 has to be dependent. But that doesn't mean that all the minimal dependent sets have to have size 3. Okay, so for example, if we look at the vector 0, 0, we know the 0 vector can't be contained in any linearly independent set. So actually, the 0 vector all by itself is also a circuit. So here we have a circuit in this matroid of size 3 and a circuit of size 1. And in fact, those are all the possible circuits of this matroid. Okay? So we can actually specify a matroid by giving a set E, a non-empty finite set E, and then the set of all its circuits, all of its minimally dependent sets. And the axioms that the circuits would have to satisfy are what we see here. So no proper subset of an element of script C is an element of script C. So that no circuit is a proper subset of another circuit. That's just because of minimality. And then there's this other axiom. So we've seen this in all of our definitions so far. There's independence, bases. There were always 2 axioms, and the second one was a little more complicated. So here, if we have 2 circuits and they share an element E, what I can do is I can look at the union of the 2 circuits, take out the shared elements, and that has to contain a circuit. That's what this is saying here. So if you have these set of circuits and they satisfy these 2 properties, then I claim that the set E comma C is a matroid where the independent sets of this matroid are any proper subsets of elements of C, right? Because the elements of C are dependent and they're minimally dependent. So any proper subset has to be independent. So for another example, this time maybe a graphic example. Suppose we let G equal the graph that looks like this. So it has 4 vertices and 5 edges. And I'm going to label the vertices A, B, C, and D. So the edges are like AB, AD, AC, and BC. Okay. So this is the graphic matroid. So E is the set of all the edges. So AB, AC, AD, BC. So that's 1, 2, 3, 4. That's AB, AC, AD, BC, and CD are my 5 edges. So what are the circuits of this matroid? So here's the one thing to remember. The circuits of a graphic matroid are the circuits are cycles, okay? So for example, one circuit is the set A, B, B, C, AC. So that's a triangle. Another circuit is the set AC, AD, CD. That's another triangle. And also, there's a third circuit here, which is the 4 cycles. So A, B, B, C, C, D, A, D. So those are all circuits. If I remove an edge, I don't have a dependent set anymore. Moreover, they're going to satisfy this circuit exchange axiom. So for example, we can see that, let's call this one, like we'll call this C1, C2, and C3. So for example, if I look at C1, which is this one, and C3, which is this one, they share an edge. So for example, they share the edge BC. So C1 and C3 share the edge BC. And if I take the edge BC out, what am I left with in the union? Well, in the union of those two, let's see if I can do this in like green or something. What I'm left with in the union is this edge, that edge, and these 2 edges. And you can see the union is not a circuit because it has this dangly edge here, but it contains a circuit, which is that triangle there. And you can check that for any of the pairs and any of the edges in their overlap. If you take out the edge, what you're left with is going to contain a circuit. Okay. So I want to show that if you have a 2-3 circuit contained in the complete graph on n vertices, then it has to satisfy this definition, 0.3. It's weird that it came out as 0.3. It has to satisfy this definition here, okay? So let's show that. And this is going to be a proof sketch because the proof is in the book. So we have to show 2 different axioms are satisfied. For the first one, suppose that C contained in Kn is a 2-3 circuit. So remember, what is a 2-3 circuit? It's a graph where if I remove any edge, it's 2-3 tight. Okay, so that means it has to have, if it's a subgraph that's on n prime vertices and it's a circuit, it will have 2 n prime minus 2 edges, and any subgraph is tight. Okay, well, since we get a 2, 3 tight subgraph, if we remove any edge of C, we know that it can't strictly contain a circuit. And none of those subgraphs contains a 2, 3 circuit because they're 2, 3 tight. We see that 1 is satisfied, right? You can't strictly contain a circuit, a 2, 3 circuit inside of another 2, 3 circuit. Let's see what happens for the second axiom. So let C and C prime be 2, 3 circuits. And let's suppose that C has NC vertices. So I'll say that, I guess, C spans NC vertices. Just means that if I have the subgraph C, there are NC vertices in it. Similarly, C prime spans NC prime vertices, and we'll say that their intersection, C intersect C prime, spans N double prime vertices, okay? So let's think about the size of that intersection. I'm gonna do this over here. If when I look at the size of the intersection, if I got two more, greater than or equal to 2n double prime minus 3 edges, well then it would have to contain a circuit. Then C, oops, sorry. What I wanted to say, if it has more than 2n double prime minus 2, then C intersect C prime contains a circuit. And that's from one of the lemmas in the book, in the Henneberg 2 section. Okay, the Henneberg 2 and Lemans theorem section, or LPG theorem. We're going to say LPG theorem in our class. And then, so we have to conclude, therefore, so that would be a contradiction. Why is it a contradiction if C intersects C prime contains a circuit? Well, C intersects C prime is contained inside of C. So if it, and we know that C doesn't contain any proper circuits. So it can't contain a circuit. So therefore, the intersection has to be small enough. So it has to be less than or equal to 2n double prime minus 3. And now let's just use the principle of inclusion and exclusion to figure out the size of the union. Okay, well, by the principle of inclusion and exclusion, the size of the union is C plus the size of C prime minus the size of the intersection. So now we're going to get a lower bound. Because C is a circuit, I know it has 2nc minus 2 edges. Because C prime is a circuit, I know it has 2nc prime minus 2 edges. And I know that the intersection has at least 2n double prime minus, or sorry, I know that the intersection has less than or equal to 2n double prime minus 3 edges. So I'm going to put 2n double prime minus 3 here. Okay, so I get that inequality. And I'm going to collect all my n's together. And so I see what I have is 2 nc plus nc prime minus the number of vertices in the intersection of the two graphs. And now if I look carefully, I have 2 negative 2's, which is a negative 4, plus 3, which is negative 1. So this here is the number of vertices in C union C prime using the principle of inclusion and exclusion. Ooh, look, I had all that extra room down here, huh? And now let's look at the size of the set that I get when I take my the union of the two cycles and throw away. I was supposed to say maybe at the very beginning. Suppose that those are 2, 2, 3 circuits, and I have an edge E that's contained in their intersection. So now I'm going to throw away that edge E, and I'm only throwing it away once. So this is going to be C union C prime minus 1. And we just showed over here that this is going to be then 2 times NC plus NC prime minus N double prime. So this should now be greater than or equal to, that's minus 1. And then there's the extra minus 1 here. So this is 2 times the total number of vertices in the union of those two circuits minus 2. Okay, so since, actually another way of writing this here is it's the same as C minus E union C prime minus E. Since C and C prime are both circuits, these are both 2, 3 tight. And then the gluing lemma from chapter 8, where we proved the LPG theorem, the gluing lemma says that if I take 2, 2, 3 tight graphs that overlap on at least 2 vertices, and since they shared an edge, these do overlap on at least 2 vertices, then either the result is 2, 3 tight, or it contains a circuit. Here I can see that it has too many edges to be 2, 3 tight. So by gluing lemma, that union C prime minus E contains a circuit. And we're done.